Welcome back. So let's talk about the same domain of strike slip, the case study as I told in the last lecture on Kangra Valley fault. Now the photograph which you see here is the damage pattern of which was resulted because of 1905 Kangra earthquake. And this was in Kangra Valley near Dharamshala. So in the basically this is in the hinterland side of the Himalayan front. So this fault was been identified. I'll talk about that in Kangra Valley, new fault, which based on the paleoseismic studies, we believe that this was the fault which was responsible for triggering 1905 earthquake. And if you look at the magnitude, then the magnitude was 7.8, and the intensity of this earthquake was felt right far away in the northeast up to Calcutta and further up to Gujarat in the west, and further west you can see northwest in Pakistan also. So this was the epicentral area. Now keeping this in mind and the damage pattern in Kangra Valley, we started looking for the signatures of any deformation, if at all it was preserved on the surface, because with an understanding that in epicentral area maximum amount of energy must have released during an earthquake, looking to the damage, because the intensity was very high and huge damage was experienced in this region, that is Kangra Valley. So with that background, we started hunting for the active fault in this region, but we were never aware, because the previous studies indicated that the Kangra earthquake of 1905 was along Jwalamukhi thrust, which is like towards the south of this Kangra Valley. So when we started looking for the active faults, before that we thought of, let us understand that what could be the reason for this region which is sitting like between HFT and MBT would have triggered the earthquake of 1905. Now if we look at this already we have discussed earlier also. So we have the detachment and the faults which are been imbricated or playing out major fault system, we see from the decollement MCT, MBT and HFT, and the Kangra Valley sits somewhere between MBT and HFT. So we have sub-Himalayas and then we have this one. We will come to that details where exactly the Kangra is located, Kangra Valley, and we will discuss about the topography also. And again with the background that most of the earthquakes now what we see are concentrated between MCT and MBT, and this portion, the frontal portion, is locked. This is based on the GPS measurements. So that also was in our mind, that whether the frontalmost fault, which as per the tectonic activity which has progressed towards south in the foreland side is the most active, then why this is locked, and whether the faults which are sitting in the hinterland may also get reactivated. So that was another idea or the question in our mind before we started this study. And this also we took into consideration that, of course, based on the earthquake data, it was been proposed that this region, that is the Kangra region in Himalaya, has already released the available slip or the energy. So this area will not be in potential area for having or hosting another large magnitude earthquake in near future, as compared to what we see here. Okay, so this marked the central seismic gap, which is marked between, or suggested as a central seismic gap between 1934 and 1905 earthquake. And further, this is also we have discussed that another gap is between 1950 and 1934 Nepal Bihar. This is Assam earthquake. Now, as I have emphasized in my previous lectures also, that we have multiple fault lines in Himalaya, and which fault was responsible in triggering these earthquakes was not very clear. Like 1905 earthquake, whether it was along Jwalamukhi thrust, or it was hosted or triggered along Himalayan frontal thrust, or it was triggered along MBT. It was not clear, but yes, of course, one study suggested, not based on the paleoseismic investigation, but based on the GPS data, that Jwalamukhi thrust was responsible for hosting this 1905 earthquake. And recent paleoseismic studies which have been carried out in central Himalaya, in Nepal, and in northeast portion of Himalaya in the Brahmaputra Valley, it suggests that 1905 and 1934, 1950 and 1934 were along the Himalayan frontal thrust. So this was again a question that where exactly, because the epicentral area or the damage or the rupture area which was been marked in published maps and all that was sitting way back away from way back north, away from the frontal part here. So many questions, we started working on this, and this map of course is the old one, but yes, of course, at least we can understand that the rupture of the large magnitude earthquakes have been given here, starting from 1555 in Kashmir, 1905 here, and the epicenters which have been marked are sitting far away from the front, Himalayan front. And then we have, this is again, it's not very clear that where was this the epicenter. Some literature shows that it is again in the hinterland side. Then we had another one which is 1505, again literature suggests that the epicenter was much away to north from HFT, but 1934 was close to the Himalayan front, and 1950, which is located somewhere here, was also along the Himalayan front. There are few paleoseismic studies which have been listed here, but none of the paleoseismic investigation. So the point here is that most of the work which was been carried out was along the Himalayan front, but no attempt was made to look at the paleoseismic history in the hinterland side. And considering that 1905 was one of the largest earthquake which took away almost like 20,000 lives at that point of time, was definitely would have been damaging one, and is one of the largest event if we compare in terms of the damage and all that. Of course, in terms of magnitude, we have this one is larger. So with this questions in mind, we moved and started looking for the first. Initially we looked at some historical data, but it was not available from this region. Then we looked at some seismic data which was published, and we found some literature which again indicated, and very unusual thing, that in this region the earthquakes with magnitude greater than 5, where we found the focal plane mechanisms, mostly those earthquakes shows the strike slip motion. So again, we were having this fault which was identified, which was strike slip, and then our more work which was been carried out along this one also indicated strike slip. So we were not surprised to see this movement that is in strike slip motion here, but no fault was been reported till we started our work here in this region. So this one is your Kangra Valley portion, and as I was talking about that, the previous research suggested that the Kangra earthquake, 1905 Kangra earthquake, was hosted by Jwalamukhi thrust. Still there is a debate whether it was actually everything was along the slip was taken up by Kangra, this, or partial slip was along the Kangra Valley fault. But we have our justifications why we say that this was the fault which was responsible in hosting the 1905 earthquake, and also triggered several more earthquakes during historic past. So overall pattern, if you take, then we have the Himalayan front here, we have multiple faults which are sitting further north or northeast from the front. So this is HFT, and Jwalamukhi thrust somewhere goes like that here, and this one is Jwalamukhi thrust, and then we have the new fault which we identified here. This marks the MBT. So this is a valley, a very large valley as compared to the valleys which we have seen like Dehradun, and then small one is here Pinjore Dun, and even Kathmandu, which is sitting here in Nepal in the eastern side. So this is quite large as compared to, and the structure also which we see is from here it swings and then take a curve here, which has also played an important role in sculpturing this Kangra Valley. So this portion we took and we started using high resolution satellite photograph with an understanding that this April 4, 1905 earthquake was with magnitude 7.8, killed more than 20,000 people and caused total damage to the towns of Kangra and Dharamshala. So we considered this as an epicentral area, and we thought that since the magnitude was 7.8, it must have resulted into surface faulting. So in spite of large magnitude and maximum intensity going up to 10 recorded in the epicentral area, no surface rupture was reported. So even the team who worked here, mostly at that time we were been ruled by Britishers, so they did study, take the survey here, but no surface rupture was reported. Now this is the Google 3D Google Earth image I took from the recent Google image. So what we see here is, this is what we are having, the higher Himalayas and very flat surface over here, and the extent of the Kangra value goes like that, and this were the two towns which were damaged extensively. Not only this, but other towns were also affected. So now if you see now, then the population is almost like more than 1.5 lakhs, and the housing or the settlement, if you look at the construction, then the full valley has been filled up, and no so if next earthquake, you can imagine that what will be the amount of damage and the people who will be affected because of this. Okay. So this is the way of construction, and what we found is that the fault runs exactly across the valley, which was unidentified. This portion marks the displaced alluvial fan surfaces. One alluvial fan surface you can see over here, and there are many small alluvial fans. Of course, the valley itself is resulted due to the degradation of alluvial fan surfaces over here. So you have the very typical flat topography of the surfaces, and which those fan surfaces are been again dissected by the streams here, and we have more other features, fluvial features we can see, like terraces and all that. So those things were been kept in mind, but we were not very sure that whether we will be able to see the strike slip here or not, but of course we were able to pick up thrust faults along this one. This is the MBT which runs here, which marks the boundary between the higher Himalayas and the Kangra Valley. So Kangra Valley, if we look at, as I told, that it is quite long and quite wide. So it is around 60 to 70 kilometers in length. If we look at east-west direction, around 4.5 kilometer wide in the western portion, 14 kilometers in the central portion, so it's quite wide, and 22 kilometers in the eastern side. And alluvial fan aggradation phase were between 78 and 30 Ka, and this work which was been done by Pradeep Srivastava and his team, and they attributed this the gradational phases. These two time zones were related to your reactivation of MBT and its associated imbricated faults. So this is the active fault trace map, which was been prepared using high resolution corona satellite photographs, and we will discuss the most prominent signatures one by one, where we have marked this yellow boxes. Okay. So fault topography has been shown here. So these are all legend has been given here. So this dashed line in red, it marks the inferred fault. We are not very confident about this, but yes, of course, there is something which could be an indicative of active faulting on the surface. Then wherever we were sure, we have marked with the continuous red line, and then the comms here which has been marked, it shows the down thrown side. So this side is down, this is up here, and that what it shows. So we have like even marked here, which we found on the surface, folding, and then the fault runs here and goes take turn displacing landforms, as well as you see the displacement or the offset of the streams, formation of the sac ponds and all that. So this is the fault topography which was been picked up using high resolution satellite photos, and then subsequently we visited field. We did very detailed field work, walked through all this interpreted observed faults, and tried to locate that in field. So this is a 3D view of Kangra Valley, and this data, which is again the Cartosat data, and the fault is running over here. This arrow has been marked with the fault runs, and very surprising thing which we were able to pick up was that we expected that in this region, because we have main boundary thrust, and main boundary thrust, if I take the topography, then what we were able to see is that this is the topography coming here, and main boundary thrust will show something like this, and then we are having the flat surface that is here, and we will be able to see the faulting something like that. Okay, so this we will be able to see the, for example, the Kangra Valley fault or any other fault which is cutting through this one. Okay, and this is your MBT. So if we take this as in north and this south, then what topography we were able to pick up here was all your south facing fault scarps, but we were not able to see this everywhere, that is south facing fault scarps. What we saw was, we are not very sure what is the fault. Probably it is almost vertical here, and then we were able to see something like that. Okay, so we in Kangra Valley fault, which we identified, it showed as north facing scarp. So what other features we were able to pick up, I'll talk in the coming slide, but before we entered into the digging trenches and all that, we wanted to understand that what in what way the environment got affected which prevailed on this alluvial fan surfaces. So you have alluvial fan surfaces here, and if this was the faulting pattern, and then so if you take this general slope of the area and then you are uplifting something here, then whatever the drainage is coming here will get blocked here. Okay. So what we will be able to see, so we used a very fundamental thing that here we should see some sort of information of ponds or ponding condition. So this was first thought process which we came with before we enter into the field. So let's see this, whether we were able to see this or not, and whether we were able to justify our thought process along this one. Okay. So this is again, this side is up and this is down, and the streams are flowing here and then getting offsetted along the fault. So as I was been talking about, so this is an Anaglyph. So we will request you to buy, if you can purchase the 3D glasses, and they come very cheap. You can buy that, and if you are having this image, you will be able to see this in 3 dimension. So you will see the terrain in 3 dimension. So, and we will also give a lecture on this, that how you will be able to prepare 3D or Anaglyph basically, and using the 3D glasses, how you can see the terrain in 3 dimension. Now this type of technique is going to help you in locating or demarcating the surface deformation or the manifestation of faulting on surface. So let's go one by one into the detail. So if you look at this part, we'll start from the western side, most prominent one, and as I told that you will the comms are indicative of the down faulting side, and but here what you see is very interesting. Okay. So you have this portion is down, this is up, but at this location this portion is up, this is down. Let's see that in field, and again it changes over here. So this is what we saw on the satellite data, that fault runs here, and very sharp linear features we were able to pick up, offset of streams here, and close up of that. Let's see that. Okay. So this portion is from here, this area. Now we are able to see in the 2D image. 2D image was also quite good, which showed very straight and sharp feature on the surface. Now this was not marked before. Even after 1905 earthquake, until 2005 this was not marked. Okay. So what you are able to see is a very beautiful sharp offset here. So this is the fault which runs. Close up of that portion you can pick up. So you have the offset of streams here, then another offset here which runs. So if I mark this line here, it goes like that. Okay. So there is an offset here. So we immediately did our detailed survey which was been carried out along this before getting into the trenching part. And what we see here is that you have a flat surface here, you have another flat surface which is sitting here. So we have, these are the 2 alluvial fan surfaces, one is sitting at greater height and another is at lower height. Now the fault has run, the arrows which have been marked here, vertical arrows, are indicating the fault trace, and this is exactly the same area which we were looking here. So this is the area, and the photograph has been taken from here. We are seeing the lower surface here, higher surface over here, and then fault goes like that. Okay. And then we see this part here also. Okay. So we were able to pick up this very sharp faulting feature, and detailed map was been prepared again using stereo pairs here. So these are the same 2 forward and after photograph of the same area, which helped us in demarcating the fault trace. So the fault runs here and we have the offset of streams here getting displaced here, and we have another star feature, and also we picked up that which side is up, which side is down here. Okay. So what it shows here, if you put, then this is down and the opposite side, so you have the fault which runs here, and this is up, and this is down. Okay. So I'll explain how this happens, and this is very typical in a strike slip environment. You'll be able to see the opposite fault scarps within a short distance. Okay. So this, if this is the north here, so this you have the north side down, south side up, and here you are having the south side down and north side up. So this usually happens because of what we call the rotational movement, and we also term this as an Caesar fault. Okay. So if I can show here, if you can, so what we are looking at, that we have the movement one, that we have right lateral movement is, of course, is absolutely okay. So the one block moves towards your side, but if you are having the block rotation like this, okay, along with the slip, if you are having that, okay, then what you see here is this is down, this is up, and this side is down and this is up. Okay. So this you will be able to see in terms of the rotation, or what we call the Caesar fault. So if you look at the topography here, this from the different angle which we have taken, so this side you see is up, this is down, this side is up, this is down. Okay. So this what we were able to pick up in the field also. Okay. So this is up, this is down, this side is up, this is down, and the fault has displaced both older as well as younger surface. So this also helps us in justifying, or at least a preliminary interpretation, that fault has remained active since long, because it has been able to displace both the younger as well as the older surfaces. Or it could be that the fault was formed, or the displacement took place after the formation of these two surfaces. Okay. So there are interpretations which you can have options with you before coming to the main conclusions. Okay. But of course, once we wanted to develop the control on the topography part. So the fault topography we wanted to map first, and then we wanted to move ahead. Now this photograph is from this portion here. So the scarp which we have photographed is from here, viewing this side. So this what you can see, and the hut is this house. Okay, this house is this one here, sitting here. Okay, so what we see is that this side is up, that is your north side is up and south is down, and that what we see here, the north side is up and south is down. Okay, and the fault scarp which we mapped, okay, with the total station was almost like 14 meter high. So this definitely is not the result of one single event, could be in multiple events. Okay, this again was an first interpretation which we did. Then offset of stream here. So this part, I'll just go back quickly, the most beautiful one which I was showing, probably, yeah, it is here. So you have this offset here. Okay, this goes like that, and we are exactly on this boundary. Okay, so we walked on this here, then we can do that. Okay, so this first dot, if I mark, is somewhere here. Okay, and then we walked along this one here, so you can have the offset here. So this was been mapped in field. So the fault is exactly which is running here, and on the section, and on the plan view it goes like that. Okay, and the displacement is that what we see. Okay, so right lateral slip. So if I put the line in blue, then you will be able to understand well. Okay, so this goes like that, and over here. So this is an offset, this is the fault trace, And now if I have to mark the based on the topography, then we have this side is up and this is down. Okay. And again with that which we were talking about the symbol that will mark, this is moving towards our side and this is moving away from us. Okay. So this is on the surface, we see the strike slip displacement and vertical over here. Okay. So this was the offset which we marked. It's almost by 10 meters. Okay. So the offset was this offset between this line and this line, it was 10 meters. I'll stop and we will continue in the next lecture. Thank you so much.